Hello everyone. In this lecture we are going to discuss about the head, power and efficiency of a turbine. So a turbine power is given by this kind of an equation where we know that power is work done per unit time or energy spent per unit time. In this case it will be work done, and since work done is force into distance, then force is again mass into acceleration, and when we rearrange we bring time closer to mass, then it's mass divided by time, then acceleration and distance are separated, and then mass per unit time is basically volume per unit time multiplied by density, and volume per unit time we know that it is the discharge, and discharge is given by written as q, and that multiplied by the density rho, and the acceleration is the acceleration due to gravity, because all the distances we have expressed in terms of head, the vertical distance, and therefore the formula finally becomes gamma qh, where gamma is basically rho into g, this rho multiplied by z, and therefore this is the equation for power of water at the turbine. But this is only the power supplied to the turbine, but the actual power generated by the turbine will be somewhat less, because there will be issues of efficiency and all those things, so we'll deal with them later. Now this term head, let's discuss what is meant by head in case of a turbine. So generally speaking, a hydraulic turbine is fitted at the bottom of a dam, and suppose this is the dam. It's a large structure, concrete structure, which is built across a river, and behind the dam the water level will rise because it has obstructed the flow of water and will accumulate some amount of head. Now there will be some depth of water in the downstream as well. So suppose this much depth of water is there, and whatever is the difference between the upstream water and the downstream water, which are called head water and tail water, head water, and this is tail water, the difference is called the gross head. So this distance or this difference between the water levels between the upstream and downstream is called the gross head. However, the gross head is not generally usable. Some head will be lost in different stages, and after losing all those we'll get the effective head, and this effective head will be different for different types of turbines. Before that, we also have to uh, we'll introduce ourselves to this thing called penstock. Penstock, which is simply the pipe or tunnel that carries water from the reservoir up to the turbine. So in this case, this whole pipe is the penstock. Sometimes in some cases when we cannot or we do not put the turbine close to the dam or toe of the dam, then we may put it someplace away from that, and in that case this whole pipe is called the penstock. As you can see, some part of the penstock is inside the dam as a tunnel in the concrete part of the dam, and other part of the penstock is simply a metallic pipe. Sometimes this pipe is carried through the hills and mountains as a tunnel, so in that case also we can call it the penstock. Now, so speaking of net or effective head of Pelton wheel turbine, as we have mentioned, the effective head will be different. The calculation of effective head will be different for different types of turbine. When we talk about Pelton wheel turbine, in that case, it is measured as the from this water level up to the level of the nozzle, and from that also we'll have to subtract the head loss inside the pipe. That means head available at this nozzle part will be equal to this head minus the head loss throughout this pipe, throughout this pipe length. Now, as we know, as water flows inside a pipe, head will be lost because of friction and all those transitions. So as soon as water enters this penstock pipe, some head will be lost as entry loss, and then continuously some head will be lost as it moves along the pipe. And therefore, if we want to draw the energy line, then it will look somewhat like this. It will be gradually decreasing as water moves along the pipe, and therefore instead of having this much head, we will at this point we will be only having this much head. So the effective head will be only this much instead of this whole amount. So this is our net or effective head in case of a Pelton wheel turbine. So as we can see, it is given as the gross head, which is the difference between the tail water and the head water. In this case, this amount. And from that, we have already subtracted this distance, which is the height of the nozzle from the tail water, because it's not going to be effective, because if we had put the nozzle somewhere around here, then we would be able to use the entire head available. But in this case, we have put this nozzle slightly above the tail water. That means we are losing this amount of head. We are not able to utilize this amount of head, and therefore we are having to subtract this from the gross head and also subtract the frictional head loss happened up to the nozzle of the penstock or inlet of the turbine. So in this case, this is the net head. Now, when we go to reaction turbines, in Pelton wheel turbines, the jet is exposed to atmosphere before it hits the turbine, and therefore after the turbine, whatever amount of head is remaining, it's not being utilized. Therefore, we are measuring only up to the inlet. However, in case of a reaction turbine, it's calculated in a different way. As you can see, the turbine is kept inside this kind of a casing, and the water is not exposed to the atmosphere throughout its path. That means from this point up to the exit point, it is not exposed at any point, and it's completely enclosed within the pipe, different parts of the pipe and the turbine casing. So at all the points, it is completely under pressure and not exposed to atmospheric pressure. So in this case, the gross head is this much, and from that we'll have to subtract the frictional head loss, which will be, as we already have seen in case of the other type, some head will be lost as it reaches the turbine. So this much is suppose the head loss, and remaining portion, only this part is the effective head, and this part is the gross head. As you have noticed here, we do not have to subtract the height of the turbine or height of the nozzle or anything, because it is completely a continuous pipe. Now that we understood the concept of gross head and effective head, let's come to the power of a turbine again. So the power of a turbine is, as we have derived earlier, it is given by gamma QH, and from the formula it is quite clear that power is directly proportional to discharge and also directly proportional to H. And therefore, in some cases, when we have less amount of water, suppose it's a small dam and the amount of water stored in the reservoir is less, so the head needs to increase if we want to have more power. And in that case, suppose we have a dam like this, and if we put the turbine somewhere around here, then we'll be only having this much head. But instead, since the river is going to flow downwards, if we can carry the water up to much lower location, somewhere around here, and here we put the turbines, then we'll have much greater head, and therefore we'll have more power. Sometimes we may not have a great amount of head, and suppose the turbine cannot be constructed downstream, it has to be constructed here only, and the height of the dam is suppose less. In that case, we'll have to push more water or allow more water to flow through the turbine, although the head is less. So in that case also, the more water, the greater discharge will compensate for the smaller head. And if we have both large amount of water and a great amount of head, then it's even better. Now coming to efficiency of a turbine, we'll be dealing with only the hydraulic efficiency of a turbine. So it is the ratio of power developed by the turbine to the power delivered to the turbine by water. So power developed by the turbine is suppose P turbine, and power delivered by the water into the turbine is, as we have seen, it is gamma QH. But this power actually generated or developed by the turbine will be, the formula will be different for different types of turbines. For reaction turbines it will be different, for impulse turbines or Pelton wheel turbines also it will be slightly different. So if you're interested, you can look at those formulas and see how they're different, why and how those equations for power are derived. Those are functions of the number of blades, the shape of the blades, and so on. So basically the power developed or generated by the turbine will depend on how efficiently the water is able to rotate the turbine. The water is already delivering this amount of power, gamma QH, but whether this whole power is used by the turbine or used to rotate the turbine will depend on the shape of the turbine blades, the number of blades, the orientation of the blades, and the blades need to be designed very carefully. Their curvature, their shape, their orientation, the number of blades fitted in a turbine, and all those things need to be very carefully decided, and lots of engineering goes into that, but that's the domain of the mechanical engineers. So, and also the friction in the bearings, it has to rotate around a bearing, which will be, as you know, those bearing balls and lubricants, all those things are there, and how efficiently those things are fitted or used will govern the overall efficiency of the turbine. And after that, it will be connected to a generator with all those coils and magnets, and there also some efficiency term will come up because some loss will be there in terms of heat, and so therefore there will be efficiency at different stages. But in our case, this is the basic hydraulic efficiency, which is power generated by a turbine divided by power delivered to it by the water. So this is all about the head power and efficiency of turbines. Now, just to give you some idea of how they are practically implemented in real life, let's show some examples This is, I'm opening in Google Earth software. This is a dam in United States of America, in Washington. That is the Grand Coulee Dam. It is one of the biggest dams, biggest gravity dams. So as you can see, this is showing the map. This was the river, and after construction of the dam, behind the dam, the river water level has risen and created this large reservoir. The actual width of the river before construction of the dam was only this much, but because we have stored lots of water behind the dam, now it has become a large, long lake like thing, which is called a reservoir. Now in the dam, as you can see, these are the penstocks or the pipes which will carry water to the turbine. And in this building, it will have all those turbines which cannot be seen from outside. You have to enter the powerhouse to have a look at the turbines. And so as you can see, these pipes are carrying the water into the turbines. There are multiple turbines in this case because it's a really large dam, and water is carried from this side. There is another example that I want to show you, which is the Hoover Dam, which is also in the United States, in the state of Nevada. And this is also a very large dam. So here also, as you can see, it's a dam. You can see the scale of the dam because these are cars traveling over the dam, and these are the intake towers through which water is collected into the penstocks and then released through the turbines. And in this case, the pipes are not running through the dam because that will compromise the structural integrity of the dam, because it's not a very massive dam. The cross section is quite thinner compared to the previous dam, and therefore the pipes are run through these mountains and they are released somewhere around here. So this building houses all those turbines, and similarly this building. So on both sides of the dam, those tunnels are carrying water and running the turbines, and the water is released after running the turbine into this, into the tailwater, which is the downstream water of the river. So this is the basics of the turbines and how they work. Thank you.